We have a little bit more to say about conditional statements. So those are statements of the form, if something, then something. So suppose P and X and Q of X and Q of X are open sentences concerning elements in the set S. They're talking about elements of the set S. By convention, an expression of the form, if P of X, then Q of X, is understood to mean the statement for all X in S, if P of X, then Q of X. So when I say if something, then something, is understood to mean that that applies to all the elements of the relevant set S. And because the idea is that these kind of things are so, these kind of expressions are so common in math that it would be, we have this sort of convention to avoid having to write so much. We don't have to write for all X and S. We just say if this, then this, and we understand it to mean that we're saying this. We're saying that this should apply to all the elements of the set. So here's an example. Consider this sentence. If X is a multiple of 6, then X is even. Okay. Now, just looking at this by itself, it's not, you don't see anything that says that this applies in all cases. It doesn't say explicitly that this applies in all cases. It just says if X is a multiple of 6, then X is even. So maybe just X is one particular value of X, right? But no, by convention, this is understood to mean that for every integer X, in this case, we're talking about integers because we're talking about things being multiples and things being even, which only applies to integers. But the more important part is the for every. For every integer X, if X is a multiple of 6, then X is even, right? So it's not just stating a fact about one number, about one X. It's saying this applies for every possible integer X. Every integer that you can imagine, if it is a multiple of 6, then it is even. Now, is this true? Is it true that for every integer X, if X is a multiple of 6, then that X is even? Well, think about what the multiples of 6 are, right? So 6, 12, 18, and so on. And you could also go in the negative direction, like 0, 0, -6, -12, and so on. All the multiples of 6 are even. So that is true. So the statement is true since every multiple of 6 is even. Here's another example. Consider this sentence. It says, if X is even, then X is a multiple of 6. What do we call this? We call this the converse of the previous statement, right? This is the converse of the previous statement. If X is even, then X is a multiple of 6. Again, the previous statement was if X is a multiple of 6, then X is even. And here we're saying if X is even, then X is a multiple of 6. Now, same thing here, right? We have a sentence of the form if something, then something, and it's talking about X. It's talking about some variable X. It's not specifically talking about one number. It's talking about all the elements of the relevant set S. Now, what's the relevant set here? Probably integers, because when we're talking about even, we're talking about multiples, that only applies to integers. So we're probably talking about integers, and we're saying that for every integer X, if X is even, then X is a multiple of 6. Right, so this is understood to mean that for every integer X, if X is even, then X is a multiple of 6. Now, is this true? Is this statement true? So it is not true. Okay, a statement is false since some even numbers are not multiples of 6. But the statement claims that for every integer X, if X is even, then X is a multiple of 6. Now notice, sometimes it does work, right? Sometimes you have some numbers that are even, and they are also multiples of 6, right? Like the number 12, it's even, and it's a multiple of 6. But this sentence is understood to mean for every integer X, even though we never said explicitly for every integer X. It's only understood, it's implied, but we have to make sure that it applies to every possible integer X. And because it doesn't apply to every possible integer, because there are some even numbers that are not multiples of 6, that are not multiples of 6, this statement is false. So the statement is false. Okay, here are a few more conditional statements just for fun. Here's an example of a conditional statement. If a list has n entries, then it has n factorial permutations. right? So for example, if a list has 3 entries, then it has 3 factorial permutations. This is a true statement. As we saw, this is based on the multiplication principle. Another conditional statement, if P is a prime number, then P is odd. Okay, now here, even though we didn't say that this applies to all prime numbers, we just said if P is a prime number, but the idea is, this is understood to mean that for every integer, if P is a prime number, then P is odd. Now, this is a false statement. It's a statement, but it's a false statement, since 2 is prime. Now, all other prime numbers are, in fact, odd. So it's kind of almost true, but it almost doesn't count, right? So it's a false statement. So because this statement is claiming, even though not explicitly, but implicitly, it's claiming that all prime numbers are odd, okay? But that's not true, because 2 is a prime number and it is not odd, it is even. One more, if a set X has n elements, then the cardinality of the power set of X is equal to n squared. Now, is this statement true? So this works out if the cardinality of X is equal to 2. All right, if the cardinality of X is equal to 2, then the cardinality of the power set of X will be 4. So that's 2 squared. So that works out, but it only works out there. But in other cases, it does not work out, right? If the cardinality of X is 3, for example, it doesn't work out. Now, here again, even though it doesn't, we never said explicitly that this applies to all sets, right? The statement never said explicitly that it applies to all sets, but we understand an if-then statement when it involves a variable like X or N. Well, here, I guess I'm not sure whether the variable is X or N, but whatever, there is some variable here. The point is, we have an if-then kind of sentence. We generally assume it applies to all the relevant things, meaning all sets of any size, not just size 2. So even though it works out if the cardinality of X is 2, it doesn't work in other cases, so the statement is false.